Okay, so in the last few lectures we discussed the notion of compactness. We discussed the notion of compactness. Right. However, as we saw, there are lots of important spaces which are not compact. However, now note that there are several important spaces which are not compact. For example, Rn. Right. These spaces are, however, locally compact. However, locally compact. Which is the next property we shall study. Okay, so let's define local compactness. Okay, so let X be a topological space. Right. So we say that X is locally compact if every point X in X has an open neighborhood U such that U closure is compact. Right. An example, it is clear that Rn is locally compact. Right, because we can take any point and we can take a disk of, let's say, radius 1 around it. So the closure will be this closed disk, and this is obviously closed and bounded in Rn, and therefore it's compact. Right. And so one of the main propositions, a very useful proposition we are going to prove about locally compact spaces is the following. So the following proposition is very useful. X is locally compact if and only if for any pair X comma W where W is an open subset containing X, we can find an open subset V such that X is in V, which is contained in V closure, and V closure is contained in W, and V closure is compact. Okay. So in other words, given any X and given any open subset W which contains X, we can find a neighborhood V of X such that V closure is compact. Okay, so this is V closure. Okay, so let us prove this. It is clear that if this condition holds for any pair x comma w, we can find V such that x belongs to V, V closure is contained in W, and V closure is compact, then X is locally compact. Right? We simply apply this condition. We simply apply this condition to the pair x comma x. Right. So when we apply this condition to this pair, we will get that there is an open subset U which contains x, and U closure is obviously going to be contained inside x, and U closure is compact. Okay. So this proves that. So that's precisely the meaning of being locally compact. So let us prove the converse. Let us assume that X is locally compact. Okay. So now recall the following assertion, so which we have already seen before. So let Y contained in X be a compact subspace. Okay, this is more general, yeah. So consider the following. More general assertion, right? So let Y contained in X be a compact subspace, right? And let X be a point in X minus Y, right? Then there are open sets, subsets C and D such that Y is contained in C, X is contained in D, and the intersection C and D are disjoint. So let's see how to prove this. So this is our X, right, and this is our Y, and this is our X, right. So for each point Y in Y, yeah, we can find a neighborhood. Since X is Hausdorff, we can find a neighborhood U sub Y of X and V sub Y of Y such that find neighborhood U sub Y containing X, V sub Y containing Y such that U sub Y intersected V sub Y is empty, right. So we can cover Y as, we can write as a union of all these V sub Y's, right. As Y is compact, this implies there is a finite subcover. Right? And then we let U be equal to the intersection of these U Y sub j's. Each U Y j contains X, so this implies that X belongs to U. U is a finite intersection of open sets, and therefore it is open. And right? So it's not we can cover. So y is contained in this, sorry. Y is going to be contained in this. And since y is compact, and from what we had seen in one of the earlier lectures, if we can put y into a collection of open subsets, then we can find a finite subcollection of that collection such that y is contained in that. So x belongs to U. Okay, so let me just, right, and let's look at, so let D be equal to U and let C be equal to this union j equal to 1 to n Vyj's, right. So this Vyj's could be something like this. Right. So then C contains y and D intersected C is equal to U intersected union j equal to 1 to n Vyj. This is equal to union j equal to 1 to n U intersected Vyj, but this is contained in union j equal to 1 to n Uyj intersected Vyj, which is empty, right. So this proves our general assertion, which is something, and we had seen the same proof before earlier as well. So we will use this general fact, yeah. Okay, so suppose now we return to the proof of our assertion. So we are assuming that X is locally compact and we want to show that X has this property. Yeah. So suppose we are given a pair X comma W where W is open. Yeah, and X is contained in W. Right. As X is locally compact, this implies there exists a neighborhood open subset such that U closure is compact, right. So this is our X, this is W, and let's say U closure is this. Right. So consider the closed subset. Y defined as U closure minus, so U closure I'll write it as minus W, but this is same as U closure intersected with X minus W. W is open, so X minus W is closed, so this is, and we are intersecting two closed subsets, so that's a U closure is compact, and compact subspace of a Hausdorff space is closed, and therefore the intersection of these two is going to be closed. So this closed subset, it looks something like this, right. So from U closure we are removing W. Right. So this region is Y. Right. And right, clearly X does not belong to Y. Right. So thus okay, so being a closed subspace of a compact space, since Y is a closed subspace of U closure which is compact, this implies that Y is compact. Right. So thus, using this general result that we proved, yeah. So thus, there are open sets C and D such that Y is contained in C, X is contained in D, and C intersection D is empty. Right. So our C could be some open set like this. So C contains Y, right, and D could be some open set like this. Right. So we can replace D by an open subset which is smaller than D as long as it contains X. Yeah. So we may replace D by D intersection U, right. So U contains X, so therefore D intersection U also contains X, and assume that D is contained inside U, right. So right. So our set D is going to be contained inside U, right. So this implies that D closure is also going to be contained inside U closure, and as U closure is compact, this implies D closure is also compact because it's a closed subspace of a compact space. Yeah. So now no point of Y can be in the closure of D, right, because if Y is a point in Y, then there is a neighborhood of Y, namely C, such that C intersection D is empty, right. So this implies that Y does not belong to D closure, which implies D closure intersected Y is empty. So as D closure is contained inside U closure and D closure intersection Y is empty, this implies D closure is contained in U closure minus Y. Yeah. And as Y is equal to U closure minus W, this implies that U closure minus Y is equal to U closure intersection W, which is contained in W, right. So thus we have found an open set D such that X is in D and D closure is contained in W and D closure is compact. Okay, so this completes the proof of the proposition. Okay, so this proposition is very useful, and this set theoretic check is very easy, and I will leave it to you as a simple exercise. Okay, so so next we are going to talk about compactifying locally compact spaces. So note the space, the open interval 0 1 is locally compact, right. So that is clear because I mean if we take this interval 0 1, then given any point x we can find a small closed interval around x, and we know that this closed interval is homomorphic to 0 1, which we proved is compact, right. Now notice that it is contained, so this interval 0 1 is contained as a dense open subset in, it's obviously contained in the interval 0 1 and also in S1, right. So to see this, note that 0 1 is homomorphic to R, and using the stereographic projection, R is homomorphic to S1 minus this north pole. So R is homomorphic to S1 minus this north pole n, right. So this implies that this is homomorphic to R and this is embedded inside S1. So although we can compactify a locally compact topological space in many ways, there is one compactification which is special among all these, and which is what we are going to explain now. So we want to compactify. So thus there can be many ways to compactify a locally compact topological space. However, one particular compactification is very special, and we shall next describe that. Okay, so we will do that in the next lecture, so we will end this lecture here.